the light bulb mystery that started it all. Berlin in 1900 bustled with the energy of a newly unified nation determined to prove itself on the world stage. The German Empire had emerged just 30 years earlier, and now its leaders possessed an almost desperate hunger to industrialize faster than their European rivals. Steam-powered factories filled the air with smoke while electric streetlights began replacing gas lamps on major boulevards. This was the age of steel and steam, of grand engineering projects and technological optimism. German engineering companies had poured enormous sums into acquiring the European patents for Edison's revolutionary light bulb. These weren't merely business investments, they represented national pride. The light bulb embodied everything the new Germany wanted to become: modern, efficient, and technologically superior. Engineering firms quickly recognized the massive profits waiting in municipal contracts to illuminate the streets of Berlin, Hamburg, and Munich. The German Empire needed thousands of streetlights, and whoever could build them most efficiently would secure a fortune. The German government understood that technological leadership required more than just purchasing foreign patents. In 1887, they established the Physikalische Reichsanstalt in Berlin, a technical research institute designed to give German industry a competitive edge. The PTR represented a new approach to industrial development. Instead of simply copying foreign innovations, German scientists would understand the fundamental principles behind them. This understanding would allow German companies to improve existing technologies and develop entirely new ones. By 1900, the PTR had enlisted Max Planck, an methodical physicist with a reputation for solving difficult mathematical problems. Planck's assignment appeared deceptively straightforward. Figure out why heated light bulb filaments change color as they get hotter. The practical importance was obvious. Understanding this relationship would allow engineers to design more efficient bulbs that produced more light while consuming less electricity. What nobody anticipated was that this simple engineering question would expose a fundamental flaw in humanity's understanding of energy and light. The mystery seemed almost trivial at first glance. Heat a piece of metal with a torch and watch it glow. First it turns dull red, then bright red, then orange, then yellow, and finally white hot. The progression appears logical and predictable. But when Planck examined this phenomenon mathematically, using the established laws of 19th century physics, he discovered something impossible. The equations predicted that heated objects should radiate infinite amounts of energy at high frequencies, particularly in the ultraviolet range. Real objects obviously don't emit infinite energy, which meant the fundamental laws of physics were somehow wrong. This contradiction became so notorious that physicists gave it a dramatic name: the ultraviolet catastrophe. The term captured their complete bewilderment at their inability to explain something as basic as the color of hot metal. Classical physics worked perfectly for calculating the motion of planets, the behavior of pendulums, and the flow of electricity through wires. Yet it failed catastrophically when applied to the simple question of why a light bulb filament glows the color it does. The practical implications frustrated German engineers. They needed to know why blue light was so much harder to produce than red light. Blue light contains more energy per photon, which should make it valuable for illumination applications. But existing theory couldn't explain why heating a filament beyond white hot didn't produce blue light.
The relationship between temperature and light color followed patterns that made no sense according to accepted scientific principles. Planck approached the problem with characteristic mathematical rigor. He collected experimental data on the spectrum of light emitted by heated objects at various temperatures.
The measurements revealed precise relationships between temperature, frequency, and the intensity of light at different colors. But when he tried to derive these relationships from first principles using classical physics, the mathematics led to absurd conclusions.
The equations suggested that any heated object should glow with infinite brightness, radiating unlimited energy across the entire spectrum. The solution came through what Planck initially considered a mathematical trick. Instead of assuming that energy could vary continuously, he proposed that energy came in discrete packets, specific amounts that couldn't be subdivided further.
This assumption allowed his equations to match the experimental data perfectly.
The energy of each packet was proportional to the frequency of light, connected by a fundamental constant that would later bear his name, Planck's constant. This mathematical breakthrough solved the light bulb mystery completely. The reason blue light was harder to produce than red light was that blue light required larger energy packets.
At normal temperatures, there wasn't enough thermal energy available to create these larger packets consistently. Red light, requiring smaller energy packets, could be produced more easily. The progression from red to white hot occurred because increasing temperature provided access to larger energy packets, enabling higher frequency light. Planck himself didn't initially understand the full implications of his solution. He viewed the discrete energy packets as a mathematical convenience rather than a physical reality. The idea that energy might actually come in indivisible chunks seemed to violate everything scientists knew about the continuous nature of physical phenomena. Energy was supposed to flow smoothly, like water from a faucet, not arrive in discrete droplets. The quantum computers that achieved breakthroughs in 2025 rely fundamentally on Planck's insight that energy comes in discrete packets. When quantum processors manipulate individual atoms and photons, they're exploiting the same quantized energy levels that explain light bulb colors. The superposition states that allow quantum computers to perform multiple calculations simultaneously emerge from the discrete nature of energy that Planck first identified in his light bulb research. The irony remains striking. Planck's investigation of this seemingly simple question about light bulb efficiency accidentally discovered that energy comes in discrete packets, launching the quantum revolution that would eventually transform human civilization. The humble light bulb, symbol of 19th century technological progress, contained within its glowing filament the key to understanding the quantum universe that powers 21st century technology. But Planck's discovery was just the beginning. His mathematical solution to the light bulb mystery would soon inspire another scientist to propose something even more radical about the nature of light itself: Einstein's heretical particle theory. Albert Einstein had been following Planck's quantum energy breakthrough with intense interest, but in 1905 he proposed something so outrageous that it challenged everything scientists thought they knew about light itself. Einstein suggested that light, which everyone knew was a wave, was actually made of particles. The scientific community had spent decades establishing that light behaved as a wave. Experiments by Thomas Young had demonstrated light interference patterns that could only be explained by waves. Scientists could measure light's wavelength and frequency with precision. The wave nature of light seemed as solid as any fact in physics. Then, Einstein proposed that light consisted of individual particles, discrete packets of energy traveling through space like tiny bullets. The suggestion seemed not just wrong, but almost insulting to the accumulated wisdom of physics. Einstein's heretical idea emerged from his investigation of the photoelectric affect, a phenomenon that had been puzzling scientists for years. When light strikes certain metals, it knocks electrons loose from the surface. This seems straightforward enough. Light carries energy, and that energy can dislodge electrons. But the experimental details created an impossible puzzle that violated everything scientists understood about waves and energy. The mystery centered on a completely counterintuitive observation. Weak ultraviolet light could easily knock electrons loose from metal surfaces, while intense red light could not dislodge a single electron, no matter how bright it became. This made no sense according to wave theory. If light was a wave, then brighter light should carry more energy, just like bigger ocean waves carry more power than smaller ones. A massive red light beam should have had more than enough energy to knock electrons free, yet it remained completely ineffective. Consider the analogy of water waves hitting a seawall. Larger waves carry more energy and can knock debris loose from the wall more easily than smaller waves. The height of the wave, its amplitude, determines how much energy it carries.
Similarly, classical physics predicted that brighter light, having higher amplitude, should carry more energy and be more effective at dislodging electrons. Yet experiments showed the opposite. Dim ultraviolet light succeeded where brilliant red light failed completely. The frequency of light mattered more than its intensity, which violated every principle of wave behavior.
Blue and ultraviolet light, with higher frequencies, could always knock electrons loose, regardless of how dim the light appeared. Red light, no matter how intense, never succeeded in freeing a single electron. The cutoff was sharp and absolute below a certain frequency. No amount of light intensity could produce the photoelectric effect.
Einstein's solution was as elegant as it was radical. He proposed that light consisted of individual particles, later called photons, each carrying a specific amount of energy determined by its frequency. Higher frequency light contained more energetic photons, while lower frequency light contained less energetic ones.
A single ultraviolet photon carried enough energy to knock an electron loose, while individual red photons lacked sufficient energy regardless of how many arrived. This particle theory explained the photoelectric effect perfectly. Increasing the intensity of red light simply meant more low-energy photons hitting the metal surface, but since each individual photon lacked enough energy to dislodge an electron, no amount of them could produce the effect. Ultraviolet light, even when dim, consisted of high-energy photons that could each knock an electron free on individual contact.
Einstein himself initially doubted his own theory. The idea that light could be both a wave and a particle simultaneously seemed to violate basic logic. How could the same phenomenon exhibit completely contradictory properties? Waves spread out through space while particles travel in straight lines. Waves can interfere with each other while particles collide. The dual nature seemed impossible to reconcile. The scientific community reacted with similar skepticism. Einstein's particle theory of light appeared to throw away decades of careful experimental work proving light's wave nature. Many physicists have dismissed the idea as a temporary mathematical convenience rather than a description of physical reality.
Even when Einstein won the Nobel Prize in 1921, the award recognized his explanation of the photoelectric effect rather than his famous theory of relativity, highlighting how controversial his quantum ideas remained. Yet Einstein's light quanta theory proved remarkably successful at explaining multiple mysteries simultaneously. The photoelectric effect was just one application. The same particle concept helped explain how light interacts with matter at the atomic level, why certain chemical reactions require specific colors of light, and how solar
panels convert sunlight into electricity. The theory provided a unified framework for understanding light-matter interactions that had previously seemed unrelated. The implications extended far beyond academic physics. Einstein's photons became the foundation for technologies that now powered the quantum revolution.
Laser technology relies on the controlled emission of photons with identical energies. Photovoltaic cells convert individual photons into electrical current using the same photoelectric effect Einstein explained. Quantum computers use single photons to carry quantum information between processing units. Modern quantum Internet protocols exploit Einstein's photons to create absolutely secure communication channels. When photons become entangled, measuring one instantly affects the other regardless of distance. This quantum entanglement,
which relies on the particle nature of light, enables quantum key distribution systems that can detect any attempt at eavesdropping.
The 2025 quantum communication networks being developed across the globe depend fundamentally on Einstein's century-old insight about light particles. Einstein's heretical particle theory of light solved the photoelectric effect mystery and complemented Planck's earlier work on energy quantization. But the solution created new puzzles that were far more disturbing than the original problems. The idea that light could be both a wave and a particle simultaneously suggested that reality itself might be fundamentally different from human intuition assumed. If light exhibited this impossible
The
dual
electron's
nature,
impossible
what about the
dance?
fundamental building
Scientists
blocks of
at
matter
Bell
itself?
Laboratories in New Jersey were about to discover that matter itself followed the same impossible rules as light. In the 1920s, researchers conducted what seemed like a straightforward experiment with electrons, those tiny particles that orbit atomic nuclei. Everyone knew electrons were solid particles of matter, as fundamental and concrete as marbles or sand grains. Yet when scientists fired electrons at a screen with two narrow slits cut into it, something impossible happened. The electrons created wave interference patterns on the detection screen behind the slits, producing alternating bands of light and dark exactly like ocean waves crashing through two openings in a seawall. This result violated everything physicists understood about particles and matter. Waves create interference patterns because different parts of the wave can arrive at the same location either in phase, reinforcing each other, or out of phase, canceling each other out. When water waves pass through two openings, they spread out and overlap, creating regions where the waves add together and other regions where they cancel out. But electrons were supposed to be particles, not waves. Individual particles should travel through one slit or the other, never both simultaneously. The experimental setup was elegantly simple. Scientists directed a beam of electrons toward a barrier containing two parallel slits. Behind this barrier, they placed a detection screen that would show where individual electrons struck. If electrons behaved like classical particles, they should pass through either the left slit or the right slit, creating two distinct bands on the screen corresponding to the two pathways. Instead, the screen showed multiple bands of varying intensity, the unmistakable signature of wave interference. The implications were staggering. For an interference pattern to appear, each electron somehow had to pass through both slits simultaneously and interfere with itself. This defied all common sense about particles and matter. A baseball thrown at two openings in a fence cannot go through both openings at once. A bullet fired at two doorways cannot pass through both doors simultaneously. Yet electrons, fundamental particles of matter, appear to be doing exactly that. Scientists initially suspected that interactions between multiple electrons might explain the strange results. Perhaps electrons in the beam were somehow influencing each other, creating collective behavior that mimicked wave interference. To test this hypothesis, researchers modified the experiment to fire electrons one at a time, with significant gaps between each electron so no two electrons could possibly interact. The results were even more disturbing. Individual electrons, fired one by one through the double-slit apparatus, still produced the same wave interference pattern. Each single electron somehow contributed to the characteristic banded pattern on the screen, as if each electron was interfering with itself. The first electron might strike the screen at a seemingly random location, but after hundreds of individual electrons passed through the apparatus, the familiar wave pattern emerged. Each electron appeared to be taking both possible paths simultaneously, creating interference between its own multiple trajectories. This phenomenon challenged the fundamental nature of reality itself. Classical physics assumed that objects exist in definite locations and follow specific paths through space. An electron should be either here or there, never both simultaneously. Yet the double-slit experiment suggested that electrons exist in multiple states until the moment of observation. Before striking the detection screen, each electron existed as a wave of probability that pass through both slits at once. The quantum mechanical explanation for this behavior introduced the concept of superposition. According to quantum theory, particles like electrons can exist in multiple states simultaneously until measured. Before observation, an electron does not have a definite position or state. Instead, it exists as a mathematical wave function that represents all possible locations and states the electron might occupy. This wave function passes through both slits simultaneously, creating interference patterns just like physical waves. The act of measurement forces the quantum system to collapse from multiple simultaneous states into a single definite state. When an electron strikes the detection screen, its wave function collapses and the electron appears at a specific location. Before measurement, the electron existed in a superposition of multiple possible locations. After measurement, it occupies just one definite position. This transition from multiple simultaneous states to a single definite state became known as the measurement problem. Modern quantum computers exploit this same superposition principle that the double-slit experiment revealed. Classical computer bits can represent either 0 or 1, but quantum bits can exist in superposition states that represent both 0 and 1 simultaneously. This allows quantum computers to process multiple calculations at once, exploring many possible solutions to a problem concurrently. The same quantum mechanics that allows electrons to pass through both slits simultaneously enables quantum processors to perform parallel calculations that would be impossible for classical computers. The double-slit experiment proved that the quantum weirdness Einstein had identified in light also applied to matter itself. Electrons, atoms, and even complex molecules exhibit wave-particle duality under the right conditions. This discovery established that quantum mechanics governs not just energy and radiation, but the fundamental building blocks of matter. The impossible dance of electrons through two slits simultaneously revealed that reality operates according to rules far stranger than classical physics imagined. These discoveries about the fundamental nature of matter would soon force physicists to confront an even more disturbing question. If particles don't have definite properties until observed, what does that mean for the nature of reality itself? The Copenhagen conspiracy. By the late 1920s, the strange discoveries about electrons and light had created a crisis in physics that split the scientific community into warring camps. At the center of this intellectual battle stood two giants of 20th century science: Niels Bohr, the Danish physicist who had revolutionized atomic theory, and Albert Einstein, whose theories of relativity had already transformed our understanding of space and time. Their conflict would rage for decades, fundamentally changing how humanity thinks about the nature of reality itself. Bohr had developed what became known as the Copenhagen interpretation of quantum mechanics, named after the city where he conducted his groundbreaking research. This interpretation offered a radical solution to the puzzling behavior of quantum particles like electrons passing through two slits simultaneously. According to Bohr's view, quantum particles simply do not possess definite properties until someone observes them. Before measurement, an electron exists in a ghostly state of multiple possibilities. The act of observation forces the particle to choose a single definite state from all the possibilities it previously embodied. This idea struck at the very heart of scientific understanding. For centuries, scientists had assumed that objects possessed definite properties whether anyone observes them or not. A rock has a specific weight, a tree has a definite height, and the moon occupies a particular position in the sky regardless of whether anyone looks at it. Bohr's interpretation suggested that quantum particles operate under completely different rules. They exist in fuzzy, indefinite states until measurement forces them into concrete reality. The implications were staggering. If observation literally creates reality at the quantum level, then the universe operates more like a vast probability cloud than a clockwork mechanism. Before anyone measures a quantum particle's position, it exists everywhere it could possibly be. Before anyone checks a quantum particle's spin, it spins in all possible directions simultaneously. The act of measurement collapses these multiple simultaneous realities into a single definite outcome. Einstein reacted to Bohr's interpretation with deep skepticism and intellectual revulsion. The idea that reality depended on observation violated everything Einstein believed about the universe. He had spent his career discovering elegant mathematical laws that described how the universe operated according to precise, deterministic principles. The notion that fundamental particles existed in indefinite states until observed seemed to reduce physics to a game of chance rather than a science of natural laws. Einstein's objections crystallized in his famous declaration, "God does not play dice with the universe." This statement captured his conviction that the universe should operate under deterministic laws, where every event has a definite cause and effect. Random probability might describe human ignorance about underlying processes, but it could not represent the fundamental nature of reality itself. Einstein believed that quantum mechanics was incomplete and that a deeper, more complete theory would restore classical determinism to physics. The debate between Bohr and Einstein played out in conferences, scientific papers, and personal correspondence throughout the 1920s and 1930s. Einstein repeatedly proposed thought experiments designed to expose contradictions in quantum mechanics. He searched for scenarios where quantum predictions would lead to absurd conclusions, hoping to prove that the theory was fundamentally flawed. Bohr responded to each challenge with careful analysis that defended the Copenhagen interpretation while acknowledging its strange implications. Despite Einstein's persistent objections, the Copenhagen interpretation gradually gained acceptance among physicists. The interpretation worked extraordinarily well for predicting experimental results and developing practical applications of quantum mechanics. Scientists could calculate the probability of various outcomes with remarkable precision, even if they could not explain why individual measurements produce specific results. The theory's practical success outweighed its philosophical difficulties. The Copenhagen interpretation became the foundation for all modern quantum technologies. Quantum computers rely on the principle that quantum bits can exist in superposition states, representing multiple values simultaneously, until measurement collapses them into definite states. The quantum processors developed in 2025 exploit exactly the same indefinite quantum states that Bohr described in his interpretation. These machines maintain particles in superposition while performing calculations, then measure the results to extract useful information. Quantum cryptography systems use the Copenhagen interpretation's measurement principle to create perfectly secure communication channels. Any attempt to intercept quantum encrypted messages necessarily involves measurement, which disturbs the quantum states and reveals the presence of eavesdropping. The security of these systems depends fundamentally on the idea that observation changes quantum reality, precisely what the Copenhagen interpretation predicted. The Copenhagen interpretation, despite its bizarre implications, had become the foundation for quantum mechanics and modern quantum computing. The debate between Bohr and Einstein appeared settled through experimental verification and technological application. Reality seemed fundamentally uncertain at the quantum level, and that uncertainty had become the key to humanity's most advanced technologies. Yet Einstein refused to surrender. His most powerful challenge to quantum mechanics centered on a phenomenon he discovered that seemed to violate the very laws of physics he had established. This phenomenon would become his final attempt to prove that quantum mechanics was incomplete, though it would ultimately provide the foundation for technologies he never imagined possible. Einstein's spooky action challenge. Einstein's most ambitious challenge to quantum mechanics emerged from his collaboration with Boris Podolsky and Nathan Rosen in 1935. Their thought experiment, known as the EPR paradox, focused on a quantum phenomenon called entanglement that seemed to violate the most fundamental principles of physics. Einstein believed this phenomenon would finally expose the incompleteness of quantum theory and restore common sense to the universe.